Good morning. What we will do today is first review a couple of the topics that we covered last time, and then get into a new topic. I'm going to use the PowerPoint this time to see if this will help. As you remember, we talked about the wave propagation in 2 dimensions, and we learned something about the cutoff frequency. Okay, so when you have a waveguide, not all frequencies at all modes will propagate. Lowest frequencies will always propagate because in the form of plane wave. But in higher mode shapes, they may or may not, depending on the frequency. Then we talked about propagation, which is what I just talked about, radial resonance, that would be the plane waves. We talked about flexible walls. As a pipe, as a sound wave propagates in a pipe, what happens if the walls are flexible? Well, they themselves can introduce some sort of a resonance frequency. So if the energy of the sound wave goes into the resonances, then it will not propagate. So this has noise control implications that we briefly touched. That's beyond the scope of this course. Now, we're not going to do it twice, but in this class we will start with the change in cross-section, transformers, silencers, and non-plane terminations. And then I will, if we have time, I think we'll have time, I'll talk about a new concept of solving these problems using transfer matrices. Just to repeat what we have done, we talked about, I'm showing these just so that you get used to the idea of a PowerPoint presentation for a class. We have a waveguide, a duct that's rigid on upper and lower sides in the extraction between 0 and L, which defines the width of the waveguide. And we are able to, of course, as always, write the wave equation that is propagating in z direction. I see now that these are small, but next time I will make these larger. You can see these, correct? Okay. Some are small, some are large, in any case. And this expression in the parentheses shows one wave traveling in the positive extraction and the other waves traveling in the negative extraction, meaning there are reflections back and forth. But there is no reflection because we assume it to be infinite in length. We can express this waveform simply as a cosine. It could have been sine. It doesn't really matter based on this phase delay. So we have an expression, R being the reflection coefficient. Do we have a controller? Okay. And K is the wave number. From the boundary conditions on the walls, we said, you have seen these before, we say that the phase delay phi x is equal to 0. And from the other boundary condition, now we have sine kx lx be 0. What this gives us is a condition, okay, for this waveform to be able to propagate, number one, kx times lx. Kx is the wave number in the extraction, and lx is really L, okay, the length in the extraction, must satisfy this m being an integer. So other waves cannot exist. Other sound waves with the wave numbers outside of these cannot exist. These are the permissible wavelengths. Because they are the permissible wavelengths, we now can write the sound pressure in terms of a sum of all the wavelengths from m0 to infinity. Okay? This is, in some ways, the harmonics of the sounds in the extraction. Now, this is the key point, okay? since K itself is a ratio of the radial frequency to speed of sound, and it is also a sum of the K-squares, sum of the squares in X and Z direction, you can now see KZ square has a condition that must be satisfied. Okay, what is KZ? It's the wave number right up here that travels in this direction. So this number, or the square root of this, must be real. If it is not real, then when you substitute it in here, it will be decaying, exponentially decaying number. Okay, so then for frequencies, omega larger than m pi over Lx times c, kz is real and it will propagate. And of course, for low frequencies, for a particular mode, it will be imaginary. We talked about propagating waves and distortion field. What that means is what I just described. Kz must be real. For low frequencies, only the plane waves propagate. What is a distortion field? A distortion field in this sense is when the geometry is an odd shape. Okay, for instance, if you have a, we always talk about nice duct or waveguide, etc. Well, what happens if you have an obstruction? Now suddenly this changes, or you go down here, you have a shape here. Okay, plane wave boundary conditions cannot be met here. So this cannot handle a pure plane wave. Waves here now have other reflections. Okay, and what does that mean? That means you have to have different spatial, space, Z and X dependence on it. That's where these higher modes come in. Okay, they have different shapes. Using a suitable combination of that, you are able to meet the geometry of the sound field. That's what's called a distortion field. It's no longer a plane wave. Okay? Okay. Now, you need to start taking notes. Today we talk about the pipes or ducts with a varying cross-section. This particular one is about infinitely long horns. What we're referring to here is a shape that comes out as a tube and then flares open. Okay, and this flaring open is such that the purpose of it is that sound is not reflected back. Okay, remember, when you have a duct or a pipe, okay, is the plane waves propagate when they come to the end of it, okay, they will reflect back. Now, this is important. Let me just have your attention just for a moment, okay? Now, we talked about rigid walls and sound completely will reflect. And we talked about resilient, pressure resilient boundaries. We said sound will reflect. It is true if it is complete vacuum. But in air, it's not really complete vacuum. So what happens is because of this impedance change, see, impedance change is because this is a large area, this is a small area. Same idea here. Okay, if you have, and we will see this, if you have sound coming through, at this point, some will reflect back, some will go through. Why is that? The impedance, what causes the impedance to change? What is the basic mechanism of that? What is different? What's impedance? Go ahead.
It's rho C, the specific.
That's, yes.
In general, it's pressure time over particle
Velocity. Okay, pressure divided by particle velocity is the impedance. And for a plane wave, that's equal to rho C. That becomes the characteristic impedance. But here, something is different. What is different? Say again?
Pressure?
Well, why is the pressure different? What do you see here? You see something. You see a change here. Cross-sectional area is changing, okay? And what does that do to the wave equation? What does it change? Continuity, okay? What does continuity mean? The amount of mass going in and coming out, okay, must be equal. And if that is the case, then particle velocity will change, okay? So you have to have a continuity. That's where S comes in. Now, the reason I mentioned this, and we're going to get back and study that, but the reason I mentioned this was just to illustrate another point here. And the point is, when you have a duct, as waves are traveling down and you come to the end of an opening, okay, what will happen? Some will have to come back because now suddenly you have a big area change. And some will leak out, okay? There will be sound radiated. That's the basis of organ pipes, musical instruments, etc. Now, when you have a loudspeaker, okay, you want to make big announcements, okay? When you have a loudspeaker, you don't want the sound to come back. What is a loudspeaker? This is the membrane that oscillates back and forth, and if you have the sound reflecting, it's going to come back and load the membrane. That's not what we're interested in. We want the sound to go out. So what you want to do is flare this out as long as you can. What does that do? Effectively, it matches impedance. Okay? Here it's a plane wave. As it goes out, it actually curves some, but then it just radiates out. So that's the reason why horns are very, very fundamental to acoustics, to help propagate sound to long distances. So in the derivations here, we assume a couple of things. Sound wave that comes in, the plane wave, is perpendicular to the axis, number one, and the walls are rigid. Okay, those are two important assumptions in the derivation of these. In our earlier lectures, probably one of the first ones, we talked about potential, velocity potential. Okay, and we defined velocity potential as they're the same. Is gravitational field, for example, is a velocity is a potential. So its derivation in this case with respect to time multiplied by the density is pressure, and its gradient in space, negative of the gradient in space, is the particle velocity. The reason we use it is it's independent of coordinates, and it takes away the directionality. It's a potential field. And velocity potential has exactly the same form. Oh, you need it? Yes. Exactly the same formal wave equation. So you can write the velocity potential as identical to the wave equation. if you replace phi, that would be the pressure wave equation, or you can have velocity potential wave equation. Okay? There's a tendency to go too fast when you use these, so let me know. Okay. Now the continuity equation, we're driving the rewriting, I should say, expressing the continuity equation for an elemental mass in the horn. Okay, let's just say a dx, an element of length dx in the x direction, and the area, the cross-sectional area, is S of x. Okay, cross-sectional area S changes with the axis. Density rho, and particle velocity v, and again del rho over del t sx. So the change in mass between the two sides of this elemental mass is balanced by the forces. Density is a first order variable, and we keep it pretty much constant and use the linearized momentum equation that we have used before. So we are able to then rewrite the continuity equation simply as 1 over s times del sv. What we have done here is take rho out, and s and v we kept together. You can see on the left-hand side, this is a partial derivative of the gradient of s times v. That's the area times the velocity. Okay, Sx is independent of time, so it comes over here, and we now have a modified wave equation. Modified, not quite there. This is the equation that we use for describing the velocity potential in a horn. You can see on the left-hand side the spatial dependence, and on the right-hand side the time dependence. Now, if S, what is S? Cross-sectional area. If the cross-sectional area did not change along the length, what would happen here? This term would disappear, and you end up with the normal wave equation. Okay? So this is the component. The first part of the left-hand side is what is brought in by the variable cross-section of the duct or the pipe. Now, this part we can rewrite in terms of a natural log. Now, the second term is what we were just talking about, okay? And that's called the Horn equation, okay? That's known as a Horn equation. And you can solve a number of different types of cross-sectional changes using this equation. Some types of variations, area changes, are amenable to exact solutions. And one of these is the exponential horn. Do you have any questions so far? All clear, more or less? Okay. Are we going too fast? See, I'm not writing. I did my writing last week, so don't want to go too fast. That's everything okay? All right. Now, let's assume that the horn now has an exponential variation. Okay, this profile here, okay, the cross section here, can be described by e to the 2k sub 0 x. Okay, there's an exponential increase up to a certain point, but we're now assuming it to be infinite. Okay, so we can say then there are no reflections from the other side, from the opening. If you substitute the value of S up in the Horn equation, okay, what we have again is a very simple modified wave equation. And for harmonic waves, where the dependence is exponential minus I omega t, okay, we can rewrite that by eliminating the time dependence as a second order differential equation.
Are you going to have these slides?
I think you should make notes. You'd like to have the slides? Well, in the future, maybe what I'll do is bring the slides, and because I'm adding things to it during the lecture, I think it's good to take some notes. I can also get the slides later too. But I think you should take notes because I modify as we go along. Okay, second order differential equation and general solutions, where S12 is written as a combination of K0 and K squared. Now K itself is, let me see, K itself is the wave number, which is this. K is the wave number, omega over c. And K0 is, just to remind you again, half of the flare constant. Flare means exponentially flaring out, okay, broadening. Okay. This could have been written in the opposite and drop I, but I did it on purpose, and you'll see the point in a minute. So the solution finally for the pressure will be, as you can see, in terms of two components. There is a, yeah, why don't you write it down and let's talk about this. Now, I would make notes on these. What do you see here? Remember, we always say, when you look at equations, it should tell you something, okay? What does it tell you? What does the first term tell you? Yes? Go ahead.
It's a propagating wave with the amplitude.
With a what?
With the amplitude A first.
Well, no, that's this. What about this guy?
E.
What does it tell you? What does it show you? What is the difference between a term like this and a term like that? Go ahead.
The first term, it attenuates.
Attenuates, yes. This is an exponential decay, right? And this one does what?
It's an harmonic.
It's a harmonic wave. Okay, it oscillates, it continues. So when you multiply them, what happens?
Harmonic waves.
Exactly. A harmonic wave with a decaying amplitude. Okay, very good. And so what we're seeing here is there's a decaying component that depends on the flare constant. Okay, if the flare constant is small, then the decay is also slow. What does that mean? If it is suddenly opened, it's very big, then it's going to decay very quickly. Okay, so it has to be a gradual flare. And then, now, what are these two again? Let's just examine them. Propagating waves, we said. Where does this propagate? Which direction?
X.
Speak up. Yeah, out. X and out, right? And where does this go?
Infinite.
Yes?
There's no infinite. There's no reflection.
There should be no reflection. So what do we do with it? What do we do with it?
I will replace infinity instead of.
B must be 0 because it's not a physically realizable solution. Okay, so there's no B, basically. Anyway, you can see now the different aspect of this is what happens. The K1 here, we have the frequency relationship. If K0 is larger than K, once again, you have a decaying, double decaying wave in some ways, okay? If K0 is larger than K. We do not want K0 to be too large to begin with because it has a decaying effect, okay? And if it is larger than K, once again, this becomes also decaying and there's no propagation. It's a cutoff frequency. As we said, for an infinitely long horn, as we assumed it to be, B is equal to 0. So there's no reflected wave. And for wave numbers less than K0, sound field just propagates out. Now, let's take a look at the impedance. Okay, the impedance of the plane wave can be expressed as just a simple set of mathematics. You can see it becomes a ratio of the particle pressure to particle velocity. Once we make the appropriate substitutions, let me put the whole thing on here. You can see the impedance is a frequency-dependent quantity. Yeah, sure.
That's K is bigger than K0, right? For
It-
sound propagates.
Let's see. K must be larger than K0 for sound to actually, let's see now, K prime, yes, it should be. And what do we have here? Okay, I think that you're absolutely right. I think it should be K larger than K0, but let me just see for a moment here. Has to be, but my notes are not right. Yeah, when you look at the equations, it should be K larger than K0. I'll check on this. Thank you very much, yeah. Yes, that's right. Yeah, it should be. Okay. Okay, so the impedance, once again, just the opposite of that. Yes, if F0 is larger than F, of course, this again becomes non-propagating, okay? So it has to be, this has to be less than 1. It's smaller than that, otherwise you have a complete cutoff. Okay. Let me put these, have you gotten these down? Yeah. The, yes, consistent is just the opposite of that. When F0 becomes larger than F, then the square root expression here also becomes imaginary, and there's no propagation. So sound is distorted. Okay. I'm going to show you in a minute the numerical results of radiation impedance for 3 different types. Do you have them? Okay. 3 different types of horns. We could talk about this for probably a week. This is a very interesting topic, interesting subject matter. But if you take a look at the possible shapes of horns, the exponential, the dotted one, is what we just studied a moment ago. Then there's a conical one, straight line, okay, all around. And then there's a parabolic shape. So you can see here we're using 100 centimeters square at 100 centimeter distance from the source. So 1 meter out the length, and 1 meter square is the opening. And 1 centimeter square is where the horn is. Okay, the opening of the horn. Now, if you take a look at the radiation impedance, how much radiation is put out, you can see the steepest cutoff is the exponential. Okay, that means from 100 hertz up it radiates more or less linearly, okay, not quite. But below that, it's cut off. There's no radiation for this particular shape. Remember, the cutoff is dependent on the flare constant, okay? And there's a cutoff. Now, you can also see, for example, for the parabolic one, how degenerate in some ways the sound radiation is, okay? Its radiation ability is really very limited. It's not very clean. At some frequencies it radiates better than at other frequencies and so on. And whereas the flat conical one also not bad, but it's not as good as the exponential horn. Now, as you're writing these, somebody asks you a question about how do I select a high quality loudspeaker like this? What would you do? What are some of the obvious things that you would like to see? How would you know the quality of a loudspeaker? horn loudspeaker, not the other types. What is obvious? What is common to all three? That's an issue. What do they do and what do they not do? Take a look at this. This is up to 10 kilohertz here, 1,000 hertz, 100 hertz, logarithmically spaced frequency spectrum. Would it have been better if this cutoff were at 1,000 hertz? $500, 5,000 hertz? Would it be a better loudspeaker? Yes, no?
Yes.
Yes? Okay, why? You just want to say yes? Why?
Best one is the third one.
I'm sorry, I can't hear you.
Best one is the third one.
Best one is the third one, but my question now is, would it be better to adjust it so that cutoff is here?
No, I don't think so.
No? Why not?
Because the speech is between 30 kilohertz and
Okay.
3.
Speech, speech actually is between 1,000 and 4,000 hertz. Speech is up here. Speech is up here. But you want to be able to broadcast all the frequencies as much as possible. What that means is you want this to be as low as possible. Okay? What does that mean, though, to make it as low as possible? What does it take to do that? You have to look at your equations and see where the cutoff frequencies are. Cutoff frequencies show in the geometry. Okay? That means you have to have really huge loudspeakers. So there's a trade-off between the quality and the configuration and the size that you can use. Okay? So to be able to bring this down to a lower cutoff frequency, the length, the opening, etc., have to be much larger.
This is the real part of the invisible.
Yes, radiated part, yes. So for high quality, the cutoff frequency should be as low as possible. And there's a time delay caused by the low frequency cutoff of the horn, and that's given by this expression. Okay, this low frequency causes a little time delay in the system. Okay, this is what I want to talk to you about the horns or pipes with varying cross-section, and then how they're applied to loudspeakers, horns themselves. Okay. Questions on this? Just very briefly, what we did was take the exponential, a varying section. We rewrote the continuity equation and used the linearized momentum. Once again, derived or redrived the wave equation, but using the velocity potential, and then we solved it. And we solved it then for a particular change in the horn cross-section. Yeah, see, that has a whole chapter on this that you're reading. Right? There is a whole chapter of different types. So you can talk about these for almost a week. Yeah, it's a good book. So we redrived this, solved it, and did do some analysis of the results. Now, what we'll do now is apply that to different types of boundary conditions at the end of a tube. Okay, so we have a tube, if it terminates in a cone, a reverse cone, an oblique angle, ending at an angle, a tubular end, or an exponential horn that's shut off. Okay? So these are different types of endings, some of which we will look at. And the question is, how do you go about solving? I'm going to ask you this question to get you thinking about this. In everything that we will drive, we'll just use this distance as d from the end of a normal or regular cross-section the moment it goes into the termination. So the termination length is d. Let me ask this question now. How would you go about solving this? What would you do here? What is the first thing you would do? Oh.
You can divide
Mm-hmm.
two.
Okay. We can write what? Go ahead.
First we divide the tube into two parts.
Okay. One part here, let's say one part there. Uh-huh.
The wave equation is different.
Wave equation is different for this. What is the wave equation here?
Something like the one.
The Horn
Yeah,
equation?
Yeah.
Mhm.
Quantified in this.
Okay. Use the Horn equation here and the regular wave equation here. And then what would you do? This is an overall plan of attack now. Okay? And then what would you do?
Then apply the boundary conditions.
Okay. These guys are writing and not listening. They're drawing pictures. Okay. Okay. Do you see what we're trying to do now? We want to understand what is the acoustic field of a tube that has a different termination than a flat termination. How would we write that equation? Okay? Now, we said let's consider two different areas. Okay, one side we know what the acoustic field should be like, and then we have another side well we don't really know. And one suggestion was, well, we can use that Horn equation, and because the area changes as a function of distance. Does that make sense? Can you apply that here also?
Not Horn equation, but the same procedure.
Same process, exactly, yes. And this is a tube, this is a tube. And here you can, of course, apply the same because area is changing with distance. In this case, exponentially, linearly, and so on. Now, what do you do then? What is the next thing? Did you hear what he said? What is the next thing? You're able.
Boundary conditions.
Well, what are the boundary conditions?
We can consider like 2 medium
Mm-hmm.
pressure and velocity. must be
Right, it's a continuity, exactly. And so you have written the field expression, pressure, velocity, field for this and for that. And what you want to do is they have to be pretty much the same where they meet. So now that you know what to do, we can go very quickly with the with the derivation. Okay, so this is the tubular part where pressure 1 is in terms of x variable cosine kx between 0 and, we say this is L minus epsilon just before it gets to the interface where they meet, only because their acoustic field is not quite uniform. To be technically correct, we say L minus epsilon. So we use the Horn equation for the second part, okay? And this could be any different type of termination. And you see here, this depends on x because coordinate is from 0 on the left all the way to L, whereas the Horn equation is utilized for the y coordinate coming from the tip, from the other end of the termination. This is identical to what we had a few minutes ago, but written in terms of pressure again. Okay, Horn equation is rewritten, and we make a number of different assumptions. Once again, we say that the pressure and particle velocity are constant in plane. So we're talking about plane waves. We have to make that assumption to drive this. And so we do have plane waves all the way in the tube and also inside the termination, and they are perpendicular to the axis. When do we satisfy that? Only at very low frequencies. Why? At high frequencies, we have different shapes, reflections, particularly at the tube end. The second assumption is we're saying that the sound field inside the termination is the same as when the termination is extended to infinity, meaning it doesn't have reflections there. So we make two major assumptions just so that you're able to use the simple plane wave equations to be able to solve the acoustic field expression for this termination. You have that? Epsilon here is epsilon 1 is to the left, epsilon 2 is to the right. And so this region, the width of that region is much smaller than a wavelength. So it's negligible. What happens there, the perturbations there are negligible. Now, yes, this is what I'm saying. So the volume between epsilon 2 on one side and epsilon 1 on the other side is so small that we assume the pressure to be, here it is, in fact, much less than lambda. Okay, so as a result, pressure is uniform in that area. That's the major assumption here. Okay, this is the what you refer to as the boundary condition now. Okay, on either side of where they meet, the pressure must be the same. That's one boundary condition. The second boundary condition must be the continuity. Okay, so again, we say compressibility of the medium has no effect on the velocity distribution. Once again, plane wave distribution, but this time we are interested in the cross-sectional areas. Okay, of course, where they meet, both areas will be exactly the same. Okay, so these are the two major boundary conditions that we use where the termination and the tube come together. Okay, where the termination and the tube, this is the exaggerated part, but come together. And then now let's see if we can apply to, there's not much else here if you have written it, but now let's see if we can apply it to a couple of different types of terminations, just as exercises. Okay. Let me just move. Let's now apply it to a conically terminated tube. Okay, this original shape that we had seen. Now, we express the area. Remember, we used before an exponential flare. Now, R is the radius from the center. Excuse me. D is the length, and Y is the distance from 0. So the area changes with y squared as it goes towards the tube. Horn equation, as before. What we do now is substitute. Once you substitute the Horn equation, it takes this form, and the solution now is a wave that has propagating and reflecting components. But as you can see, it decreases with distance from its apex as 1 over y. So we have to be a little bit careful about the boundary condition that we choose here. The apex, the point at the tip of it, is a singularity. Okay, we don't know the exact values of sound pressure and particle velocity at the very tip of this cone. But we also know that there's no source there. Okay, so what that suggests to us then is an equivalent value to a boundary condition. That says y squared, or area squared, times particle velocity as it goes to the apex is equal to 0. Okay. Why don't you write this down and let me explain the physics of what that means. Okay. Take a look at this expression here, please, just for a moment. Once you substitute an area expression, as I've shown up there, you have a pressure expression that gives you a value that is inversely proportional to y. Ordinarily, what that means is as you go out, pressure decreases. As the area opens up, pressure decreases. Okay, but it also says that y is equal to 0, it's infinity. Okay, a singularity. But we know that there's no source even there, so it cannot be infinity. Okay, so what we do then is, because there's no source at the apex, you have to realize that an area times velocity, the flow out, has to be 0. And that is the same as saying, that's the area, same as saying y squared times particle velocity must be equal to 0 as y goes to the apex. Okay? And so you finally end up with a boundary condition that you can apply to this to evaluate the values of the constants. Okay. That make sense? Okay. And that gives us the value for d plus E equals to 0. And if they change signs, you can see this now becomes a value sine ky over y. Now we come to the continuity equations that we spoke about. Remember, the tube itself had a cosine field, A cosine kx, okay, on the left-hand side, and the right-hand side was sine ky over y. Okay. So by setting the equations given above, evaluating them at L for pressure and for particle velocity, we have two equations, and their division gives us the eigenvalue equation for the system. Okay, this is what's called the eigenvalue equation, but it gives us the resonances in a tube like this, and the resonances depend on KD or D and L. That's simply. Now, a simpler equation is the tubular termination. This you know what to do, right? It's a lot simpler. One writes the sound field in the tube as cosine, and in the termination also it's a cosine field. Okay. And continuity is satisfied by evaluating the pressures at the interface and particle velocities at the interface and dividing them. You once again have an equation for the eigenvalues. Now, I distributed the homework for next week, and I'm going to add to it the next slide as the third problem, as soon as you finish writing this. And for an oblique wall, I'll get back to it in a second. Would you write this down? For an oblique wall, a tapered wall, the eigenstate equation, eigenfrequency equation is tangent KL plus the ratio of J1 to J0 KD. J1 and J0 are Bessel functions of the first and zeroth order, respectively. Okay, J1, J0, first and zeroth order Bessel functions. See if you can derive this. If you're able to derive this, you understood this lecture. Okay? I'll leave this and we'll take a break for a few minutes. And if you have any questions, I'm happy to answer. Then we'll move on to abrupt change, the details of this.